So let's examine the salicylic acid spectrum in greater detail. This is the spectrum taken in chloroform D. If we zoom in tightly on it, what you see now is a doublet, a triplet, a doublet, a triplet, but you can already see that there are much clearer patterns going on as well. Doublet of doublets, what appears to be a doublet of triplets. If we zoom back out, we have similar behavior going on here, although this is starting to be much more complicated. If we look at the ChemDraw version of this, again, B and C, whatever relationship exists between the two peaks in B will define for us which of these peaks is in fact C. Whatever coupling value exists between D and E will show up between this doublet and one of those two peaks. And so now we can go ahead and search for that coupling value. So returning to the salicylic acid spectrum and in chloroform, we should zoom in now on the peak that we know to be peak B based on a chemical shift analysis. So knowing that it is peak B, we can now figure out what coupling constants are buried within. Using the crosshair tool and measuring from the height of the first peak to the height of the second peak, what we see is a 1.7 Hertz coupling that is contained within this doublet of doublets. Namely, it is the smaller of the J values in the doublet of doublets. The second J value can either be measured from the top of the first peak to the top of the third peak at 8.05 Hertz, or alternatively from these peaks at 8.08 Hertz, or from the bottom of the trough to the bottom of the trough, and again, roughly 8 Hertz. Let's record this information in ChemDraw, and we have now identified that peak B contains a 1.7 long-range coupling, which would be between B and D, and we have a 8.0 close-range coupling between B and C. Note that this is directly analogous to the picture we had before, where we have a peak centered around 7.93 that is split by an immediate neighbor with a coupling constant of roughly 8 Hertz, but that the doublet contained within is split itself by a longer range coupling that is smaller and therefore 1.7 Hertz. In other words, the B to C coupling is this one, the 8 Hertz coupling, whereas the B to D coupling is going to be the longer range and therefore smaller intensity 1.7 Hertz coupling. Knowing that this is the breakdown, we can then return to ChemDraw and make the appropriate notations. What this now allows us to do is to go searching for those coupling constants in the spectrum, and when we find them, we can now specifically assign them to C and D. Having said that, you really should get in the habit when you're looking at a spectrum of actually examining the easiest peaks first. So the easiest peak to interpret is going to be the one where we know which one it is by chemical shift, and therefore we can establish what the other J values are. But I'll remind you that if we have identified B as this peak by chemical shift, then we also know that this peak right here must be E on the basis of the fact that it is the only other doublet present. So rather than zooming in on the triplets, we should now, in fact, examine E closely and see what we see. So let's zoom in and use the crosshair tool, and for this, the easiest place to measure for the large coupling constant is almost certainly going to be from this trough to this trough, and I will note that this distance appears to be 8.4 Hertz. So let's make that notation back here in ChemDraw. The easiest place to search for the smaller coupling constant in this spectrum is almost certainly the small trough to the small trough, which is 1.13, and just to verify that that's true, I should examine it on the other peak, and sure enough, it's 1.13. That same distance should show up as being here to here or here to here, just to make sure that we're not doing anything particularly wrong. Therefore, if we go back to ChemDraw, the smaller of the two coupling constants in this doublet of doublets type peak is 1.3 Hertz, and I'll make that note too. Returning to the picture that we're building over here, if we can identify an 8.4 Hertz coupling in the spectrum, it is clearly going to be due to the E to D coupling, and of course a 1.1 Hertz coupling in the spectrum is going to be due to E to C. And again, note that the pattern of a doublet of doublets is arrived by having a larger coupling, say 8 or 8.4, and a smaller coupling, say 1.7 or 1.1. So both peaks will have that general pattern of a 4-line pattern with a larger coupling constant and a smaller one, or a larger coupling constant and a smaller one. By now having identified the coupling constants present in both B and E, we can then go ahead and look at the rest of the spectrum and identify which peak is C and which peak is D. We learned the red information by looking at peak E in the NMR spectrum, and we found that there is a 1.1 Hertz coupling between peak there and the peak there. We can learn that there is a 1.1 Hertz coupling by looking at the first peak to the third peak in each of these, or by going from the trough to the trough. So we know that there's a 1.1, 1.2 Hertz coupling in this doublet of doublets, and you also know that there is a larger 8.4 Hertz coupling going from there to there. Therefore, again, learning as we have that the larger coupling must be between D and E, we know that D should have a 1.7 Hertz long-range coupling between B and D, and it should have an 8.4 Hertz coupling between D and E. By the same token, C must contain a 1.1 Hertz coupling to E and an 8.0 Hertz coupling with B. Finally, there's one coupling that we have not yet found in this spectrum, but which must exist. C to D must be coupled together, and there's going to be another coupling in here somewhere that is in the general range of 8-ish Hertz that will specifically be due to C to D. So we will find that now when we look at the triplet type peaks in the NMR spectrum. So returning to the NMR spectrum, if we now look at all of these peaks, I'm simply going to zoom in on this triplet here. And depending on what we see for its coupling constant, it will tell us which peak it is. So there should be two coupling constants in here due to the peaks that we've already looked at, and a third coupling constant that shows up due to the peak that we have not yet examined. Notice from here to here is a 1.7 Hertz coupling, and that should be the same as if I measure it on the other side, a 1.7 Hertz coupling. Looking at the possibilities, of course, what we have now identified is that this first triplet in the spectrum must be peak D. It has a 1.7 Hertz coupling in it. What we can now learn from this, and we can make a prediction, is that there must be an 8.4 Hertz coupling somewhere in this peak as well in order for our prediction to be true. For ease of measurement, I'll select the top of this hump and the top of this hump, and you see that sure enough there's an 8.4 Hertz coupling in there. Of course, this distance is the same, and there's also an 8.4 Hertz coupling in here as well. What does that mean? We have correctly identified peak D, and it is the furthest left triplet in the spectrum. By definition, then, if this is peak D, then this peak over here must be peak C, and therefore it must contain a 1.1 Hertz coupling as well as an 8.0 Hertz coupling. So let's zoom in on this and, in fact, verify it. The 1.1-ish Hertz coupling is very easy to spot. There it is, from first peak to the first peak there. And again, for ease of measurement, I'll go from the sharp peak there to the sharp peak here, and you'll see that we have an 8 Hertz coupling in the spectrum as well. So once again, we have made a prediction and found it to be true. This last furthest right triplet in the spectrum must be C. It has a 1.1 and an 8.0 Hertz coupling within it. So to recap, in this first peak what we found was a 1.7 Hertz coupling and an 8 Hertz coupling. From the chemical shift, we knew that that furthest left peak must be B. We then found that this peak here contained the 1.7 Hertz coupling, and therefore it must be D. This peak here, by analogy to the fact that it was a doublet, was peak E, and it contains a 1.1 hertz coupling, which therefore forces this triplet to be C. By the same token, there's an 8.0 hertz coupling that shows up in B that is showing up in C, and there is an 8.4 hertz coupling that is showing up in E that is also showing up in D. The last thing we need to identify is the remaining coupling. C and D must be coupled together, therefore there must be some J value that is shared between this peak and this peak, between peak C and peak D. If we now zoom in on this peak right here, which we know to be D, and we simply use the crosshair tool and measure from here to here, which is to say the medium distance in this peak, what you see is a 7.2 hertz coupling. That is the same as if you measure it this way. If we zoom back out and now zoom in on the other peak of interest, and again do the same measurement, going from first peak to third peak here, what you see is a 7.2 hertz coupling. Or if you go in this direction, you also see a 7.2 hertz coupling. So now we have successfully identified all of the couplings in the spectrum, and in fact, this entire spectrum now makes sense. B is coupled to C in a short range 8 hertz coupling. B is coupled to D in a long range 1.7 hertz coupling. C is coupled to D in a short range 7.2 hertz coupling. C is also coupled to E in a 1.1 hertz coupling. D and E are coupled together with an 8.4 hertz coupling, and the entire picture makes sense. The last bit of drawing I want to do for you is back in Paint, and we're going to build the coupling pattern for C and D. Let's suppose that we're working with peak D, which is to say it shows up at 7.52 parts per million in the spectrum, and it is located at this position here. So this is proton D. So we have a 7.52 singlet because at the moment it has no neighbors. Now let's contemplate what happens when we build in its neighboring interaction with proton B. That is a 1.7 hertz coupling, so we can go ahead and draw in what that would look like. Once we have added the coupling contribution from peak B, this is now a doublet with a 1.7 hertz coupling in between it. In other words, this distance right here. Of course, we also happen to know that D has an interaction with the neighboring C, and that the strength of that interaction is 7.2 hertz, so I've labeled that as such, which forces this peak to now be a doublet of doublets with a small 1.7 hertz coupling and a medium-sized 7.2 hertz coupling showing up within it. So we have a doublet of doublets, small, and a medium coupling. And finally, we know that peak D also has an interaction with peak E that has an 8.4 hertz coupling associated with it, which is to say a larger interaction than the ones we've drawn so far. And as you can see, I'll be using a slightly larger version of the same type of coupling to build this next picture. And you can see that as these purple lines are being drawn in, how you might be arriving at a pattern that looks like this. So I'll go ahead and build those slowly so that you can see them take place. Just going to go ahead and add in each single one of these lines, and notice that each of these lines is equal in intensity because what we've done is split a single peak 3 different times with slightly different coupling values. And when you're done with this, what do you see? Well, you see a 2-line pattern there, followed by 4 lines, maybe with the 2 middle lines being on top of each other and bunching up to be a little bit higher, and then another 2-line pattern there. What does this look like? Well, what we have is a 1.7 hertz coupling that's showing up between these two out here, and that's due from the original long-range coupling that we contemplated between D and B. So this distance here carries through all the way. It shows up there, and it also shows up here. And though it's harder to see, it also shows up between these 2 lines and shows up between these 2 lines. Meanwhile, in blue, we have the coupling between D and C, which is a 7.2 hertz coupling. And that distance is a little harder to keep track of and to spot, but it's between line 1 and line 3 in the spectrum, or counting from the other side, line 1 and line 3 in the spectrum. So that's the 7.2 Hertz coupling that was due to peak C and peak D. And the final coupling constant that shows up in here is between peak 1 and line 4 in the spectrum, in this peak, so line 1 and line 4, and that is the 8.4 Hertz coupling that is due to D and E. So this is the largest coupling in the entire thing, and it shows up between line 1 and line 4. Incidentally, this will always be true. There are always interesting J-values to be found between the first two lines in a given peak. And usually there's also going to be something interesting to be found looking at line 1 and line 3. Frequently there's also then something interesting to be found measuring from line 1 to line 4. This particular peak ends up being a 1, 2, 3, 4, 5, 6, 7, 8 line pattern where two of the lines end up on top of each other. So in the spectrum itself it looks like a 1, 2, 3, 4, 5, 6, 7 line pattern, but it's really an 8 line pattern where two of them line up on top of each other. And you can measure an interesting J-value from line 1 to line 2, line 1 to line 3, and line 1 to line 4. And those J-values are due to the long-range coupling between D and B, the short and range coupling and stronger between D and C, and then the strong short-range coupling between D and E. Those three lines make this peak overall a doublet of doublets of doublets, which should be an 8-line pattern that happens to line up in such a way as to be a bit more confusing and to be something that you might refer to as a doublet of triplets. But it's really not. It's a doublet of doublets of doublets. I hope that this has been a useful exercise so far, and one that you could follow, where we have a doublet of doublet pattern, B. So this is actually the peak at 7.93 or thereabouts, followed by peak D, which shows up at 7.52 in the spectrum. Then we have peak E, which is showing up at 7 in the spectrum, almost exactly. And the final peak in the spectrum is peak C, which is showing up at nearly 6.93. So there you have it. That's salicylic acid, at least as taken in chloroform and analyzed as such. You may recall that when we first encountered the salicylic acid spectrum, that the acetonitrile D3 version of the salicylic acid spectrum was subtly different. And if we look at the range between 7, 8, and 7, essentially, you see this pattern where we have a doublet of doublets, something complicated, almost certainly a doublet of doublets, and then something really weird that doesn't look like anything we've seen before. So what's going on here? Well, first and foremost, when you change solvents, what that should do is change things ever so slightly. In general, the chemical shifts environment will be the same regardless of solvent, but there may be subtle differences, and if a peak that was at 7 slides down ever so slightly, and a peak that was at 6.93 stays the same, then maybe they end up overlapping with each other. Whereas a peak that started at 7.93 has now scooted ever so slightly this way, and a peak that was at 7.52 has stayed the same. So this analysis that we performed is probably still mostly accurate for a different solvent, but if things shift in just the right way, you can end up with something that looks a bit more complicated. So, for example, we originally saw that peak B in chloroform was a doublet at a certain level of zoom, and peak C was a triplet at a certain level of zoom, and peak D was a triplet, and so on. Of course, we know this isn't true. We know that this is a doublet of doublets. We know that the pseudo-triplets are really doublet of doublets, and so on. But, again, this is first and foremost a doublet, this is first and foremost a triplet, and this is two peaks that happen to be lying on top of each other. We should be able to see that the peak at 7.93 doublet of doublet with those coupling values still exists in the acetonitrile spectrum, but it may be subtly different. For example, it is not at 7.93 anymore, it is at 7.85. Is that a meaningful difference? Not really. It has two coupling constants in it. One is at 1.8, and the other is at 8.0. Again, measuring from the first to the third makes sense, and that's at essentially 8.0 rounded. First to the third, 8.0 rounded. Trough to trough is basically 8. So that is the same peak. It has the same values. It has slid ever so slightly, 0.08 ppm to the right. But in all other intents and purposes, it is the same peak. Now, if we go ahead and zoom in on what we know to be peak D, you notice that the shape has changed ever so slightly, but once again, it's at 7.5 and change, 7.52, 7.52 rounded, and we have probably similar coupling values hidden within. A 1.8 hertz coupling, so it really is D, and if we measure from that line to that line, it's a 7.3 hertz coupling, as you'd expect. In order to make things easy to measure, I'm going to select this peak to this peak because they're both nice and sharp, and there's your 8.4 hertz coupling. This is exactly like what we said it was, 1.7 or 1.8, 8.4, 7.2. The peaks really are the same. Therefore, what should we make of this mess of 4 peaks right here? What's going on? Well, almost certainly what we have is overlap between peak C and E. And by analogy to the chloroform spectrum, you probably imagine that what happened is the doublet part of the peak was the one that shifted down ever so slightly, and the triplet part of the peak has stayed put at 7.93. We can do some complex analysis there, but what I really want to focus on is how this peak came to have this pattern. If you just ignore all of the complicated splitting and simply consider what they look like, peak C we knew to be a triplet around 6.9, and peak E we knew to be a doublet around 7.0. So what happened as we changed solvents is that this peak here in red, the 7.0 peak that was a doublet, started scooting ever so slightly to the right and ends up coming to rest somewhere around 6.96 or thereabouts. And the two peaks managed to snuggle up so close together that they started to overlap. 6.96 and 6.93 mean that these two peaks overlap, and the overall appearance when all is said and done is precisely this. The red and the blue peak together end up combining to make a purple peak that's tall enough that what you have is now this pattern that looks, generally speaking, like this. So, knowing what we know in a different solvent, we can now take a look at this spectrum and deconvolute it. This technique of being able to understand what's underlying the peak that you're looking at is necessary for the salicylamide spectrum. And if you don't have the different solvent, then you can't ever be sure that this is what you're looking at, but it's still possible. So we've covered a lot of ground in this video, and we've discovered a lot of interesting things about splitting. It's not necessary for you to know all of these at this point, and we've covered more ground than you necessarily need to know until the end of the semester when you're going to revisit splitting, and it will all hopefully make more sense. But for now, just be aware that there are such things as strange splitting patterns because you're going to see them in the lab, and that especially when you have long distances between peaks, ordinarily you can ignore them, but you can't necessarily ignore them if you have a double bond or a ring type structure in the way. Naturally, you expect that neighboring protons, such as these two, would have a coupling constant between them, or for example, between this peak here and this peak here. Those two hydrogens, those groups of hydrogens would have a normal close range coupling. However, it's also possible for peaks to have a longer range coupling, say between those and those, or between, say, those two sets of hydrogens right there. Be advised that this can happen, and when it happens, you invariably get this complex splitting because the closer range coupling is always going to be bigger, and the longer range coupling is always going to be smaller. In fact, the longer range coupling can be so small that you don't even see it, which is partially why most spectra tend to be better behaved than the ones we've been looking at today. In addition, you should remember that if you have complicated spectra, that they can look quite different in different solvents just because of very subtle shifts in chemical shift. If two peaks happen to line up on top of each other, they can have quite different appearances. And the other piece of information that I'd like you to remember is when you have a double bond, you will have a different coupling constant between the cis type protons versus the trans type protons. And just as these arcs have shown, this coupling constant will always be relatively small, whereas the blue coupling constant is going to be much, much bigger. But those are relative terms. This is a small coupling constant. This is a big coupling constant, 17 hertz or so, 10 hertz or so. But when you have protons that are on the same carbon, that, generally speaking, ends up being a tiny coupling constant. These two right here, because they're on the same carbon, will have a tiny coupling constant on the same scale as small or big. So when you look at compounds that have this general shape, they will all generally have the spectra that we talked about earlier. When you look at compounds that have a 1-2 arrangement around a benzene ring, they're generally speaking going to look like the salicylic acid and aspirin spectra that we've looked at so far. If you remember nothing else from this talk, please remember that similar structures give rise to similar NMR spectra pretty much as a rule. The rules that govern NMR spectra are the same in similar type compounds, so they should all behave very similarly.